Good morning and welcome to our fifth lecture on statistical mechanics. Today we will talk about statistical ensemble. You see, our measuring instruments have finite resolutions and they effectively perform averages over time intervals that are small on a macroscopic scale but large compared to the collision time. The basis of the statistical method is the assumption that this time averaging can be replaced by an average over a suitably chosen collection of systems called a statistical ensemble. Let's try to understand this in this way that suppose we have a system and we measure a physical quantity exhibited by this system or physical property exhibited by this system, let's say f. So f is a physical property exhibited by this system. Now we want to measure it. If we use any instrument to measure this physical quantity exhibited by this system, the instrument itself measures an average value of f, because there will be small fluctuations in the value of f with time. So the average value of f is returned by any measuring instrument. Or let's say there is a person who is performing experiments to measure this value of f at different time. So the values that he obtains are, let's say, f1, f2, f3 and so on, and let's say fn. So what do we do? How do we find the average value of f? We add them up and divide by the total number of observations n. So f1 plus f2, f1 plus f2 up to fn divided by n. That is the average value of f. So that is one way. This is the time average. This is how time average of a physical entity exhibited by a system is found out. Now there may be another method. Suppose we take a large collection of the identical system. This system A, all these are copies, mental copies of system A, and we have a large collection of that. Remember, these are only mental copies. Means the macroscopic state of all the systems will be same, but all of them at any given moment of time will exhibit f1, f2, this may be exhibiting f2, f3. So all these different systems will be in different values or exhibiting different values of f at any given moment of time. And if an observer finds all these values at one instant, he can again find the average, which we will call statistical average. So what we believe is that this time average of the physical entity f and the statistical average of the same physical entity, which we find from an ensemble of that system A. Ensemble of the system A will mean a very large number of, or collection of very large number of mental copies of the system A. So what is an ensemble? Or what is statistical ensemble? In physics, an ensemble is an idealization consisting of a large number of virtual copies of a system considered all at once, each of which represents a possible state that the real system might be in. In other words, a statistical ensemble is a probability distribution for the state of the system. This concept of an ensemble was introduced by Gibbs or J. Willard Gibbs in 1902. So now, if we consider an ensemble of systems, that is, the given system along with a large number of mental copies of it, then at any time t, the various members of the ensemble will be in all sorts of possible microstates. Indeed, each one of these microstates must be consistent with the given macrostate, which is supposed to be common to all members of the ensemble. Suppose we have a system whose macrostate is defined by EVN. E energy, V is the volume, N is the number of particles within that system. This system will have access to a number of microstates corresponding to this macrostate. So when we consider an assembly of identical systems where all of them are in the same macro state, we believe that within that system, within that collection of systems, different members of that collection will be in all possible different microstates available to the system which is in macrostate defined by EVN. So now if you consider a collection of large number of identical systems, all of them will be in the same macrostate defined by EVN. But at the same moment of time, in all probabilities, different systems or different copies of the system will be in different microstates available to the system, the actual system, in this particular macrostate. So at any given instant of time, all these copies, which are called members of the ensemble, will be exhibiting slightly different values of any physical entity exhibited by the system. So at that instant of time, if you take the average of all those values of physical entity exhibited by different members of the ensemble, the average will be same as we find by observing the single system at different moments of time and finding that physical entity. In the phase space, the corresponding picture will consist of a swarm of representative points, one for each member of the ensemble, all lying within the allowed region of this space. So as time passes, every member of the ensemble undergoes a continual change of microstates, and correspondingly, the representative points constituting the swarm continually move along their respective trajectories. So, the overall picture of this movement possesses some important features which are best illustrated in terms of what we call a density function. Density function or density distribution. Density distribution. This density function or density distribution, represented as rho, a function of r, p and t, may be understood as a function that at any time t, the number of representative points in the volume element D3R, D3P. We are redoing it. This density function or density distribution is a function such that at any time t, rho is the density function or density distribution, a function of r, p and t, is such that at any time t, the number of representative points in the volume element D3n R D3n P. Basically that will be dr1, dr2 up to dr3n into dp1, dp2 up to dp3n. So at any time t, the number of representative points in the volume element D3nR, D3nP around the point Rp of the phase space is given by the product rho Rpt multiplied by the volume element D3nR, D3nP. So this we can take as dn, where dn is the total number of representative points present at the moment t within the volume D3nR, D3nP. So clearly the density function or distribution function rho symbolizes the manner in which the members of the ensemble are distributed over all possible microstates at different instants of time. It is function of time. Rho in general will be a function of time because it is function of Rp and T. Suppose F is a physical quantity which is function of R and P. Then systems in different microstates which will be having different Q and P combination will exhibit different value of this physical quantity at any moment of time t. So if you want to find the average value of F, we can find it by this equation where we take F function of R and P into rho function of R, P and T and volume element D3n R, D3n P. We integrate for the whole range of distribution divided by integral rho R P T D3n R D3n P. The integration in the numerator and the denominator will run for all possible values of R and P. This means the integration extends over the whole of the phase space. However, it is only the populated regions of the phase space where rho is not equal to 0 that really contribute, because the region of phase space where rho is 0 will not contribute anything, neither for the numerator nor for the denominator. We should remember that the way we have defined this average, in general, the ensemble average may itself be a function of time because we have kept rho as a function of time. So this average value may itself be a function of time. At different moment of time, the average may come different. But that is because rho is taken as a function of time. When rho is fixed, when rho stops changing with time, then the average will also not be a function of time. We should also keep in mind that the members of the ensemble, which are mental copies of the system, do not interact with each other. There is no interaction between individual members of the ensemble. As the system approaches thermal equilibrium, the ensemble evolves into an equilibrium ensemble with a time-independent distribution function given by rho, a function of P and R only. The ensemble average with respect to rho PR then yields thermodynamic quantities. We assume that this distribution function rho PR depends on PR only through the Hamiltonian. The dependence of rho on PR is through the Hamiltonian. And we denote it now by rho, a function of Hamiltonian, which itself is a function of P and R. Now this automatically makes it time independent because Hamiltonian is a constant of motion, as we have seen in our classical mechanics course in semester 5. So Hamiltonian is a constant of motion. That's why when we write rho as a function of h, which itself is a function of P and R, rho becomes time independent. An ensemble is said to be stationary if rho does not depend explicitly on time. That is, at all times, if dou rho by dou t equal to 0, an ensemble is said to be stationary. So, for stationary ensemble, the condition to be satisfied is that dou rho by dou t should be 0 for all time to come. And in that case, now one can see that f, which is function of R and P, will be averaged through this equation, integral f function of Rp. Now rho is function of R and P only, d3n R d3n P divided by rho Rp d3n R d3n P. Obviously this average of f will be independent of time because now rho has become independent of time. Naturally, a stationary ensemble qualifies to represent a system in equilibrium. So, a system in equilibrium will be represented by a stationary ensemble. Now, let's determine the circumstances under which dou rho by dou t will be 0, and we will use Liouville's theorem for the purpose. Let's consider an arbitrary volume tau in the relevant region of the phase space, and let the surface enclosing this volume be denoted by sigma. So this surface enclosing this volume tau is sigma. So now if you write the rate at which the number of representative points in this volume increases, rate of increase of number of representative points representative points, or these are the system points within this volume, will be given by dou by dou t of integral over tau rho d tau. D tau is the elementary volume. Basically this d tau is d3n r into d3n p. So rho d tau is the number of representative points within volume d tau, and rate of change of this quantity with time will be the increase in the number of representative points in the volume d tau, and when we integrate it over the whole volume tau, that represents a rate of increase of number of representative points within the total volume tau. So this is the rate of increase of representative points within the volume tau. Now the net rate at which the representative points flow out of the volume tau across the bounding surface sigma will be given by the integral over the total surface sigma rho into v dot n cap d sigma. Rho is the density distribution or distribution function. V is the velocity of the representative points or system points. N is unit vector normal to the area on the surface sigma. So if we draw an elementary area over this surface, say that is d sigma, and this is the unit vector normal to that area. So this is d sigma. Then if the velocity of system point is along this direction, so that will be the direction of velocity v. So v is along this direction. So if this is d sigma, then number of representative points coming out of this area d sigma over here will be in an interval dt. It will be the representative points within this volume. So in an interval dt, if we take this distance v dt, then within this volume v dt into d sigma, whatever is the number of representative points will come out of the surface d sigma in an interval dt. So when we are trying to find the number per second, dt is 1, and only those particles will be able to come out of this surface d sigma which have a velocity component along n cap. So that's why v dot n cap, that is velocity component along n cap, multiplied by d sigma, that is the effective volume from where the particles are coming out per second. And how many particles are coming out? That volume multiplied by rho. So rho into v dot n into d sigma represents the number of particles, or number of particles here means representative points or system points. So number of system points coming out of that surface d sigma per second will be rho into v dot n d sigma, and when we integrate this quantity over the whole surface sigma, that is total number of representative points flowing out flowing out of the total surface, total bounding surface. Per second. We will keep in mind that this v vector is the velocity vector of the system points or representative points in the region of the surface element d sigma, while n cap, that is the outward normal unit vector. Now, using divergence theorem, this can be written as integral over the volume tau, divergence of rho v vector into d tau. D tau is d3nr, d3np. So, the number of representative points entering the volume tau per second is given by dou t of the integral over tau, rho d tau, and number of representative points leaving the volume tau per second through area sigma is given by integral over tau, divergence of rho v into d tau. We should remember that as the coordinates that we are taking here are r and p, this divergence will have a different meaning. You see, divergence rho v, v is in terms of r and p. So, divergence rho v will mean basically integral, rather summation over I from 1 to 3n and dou by dou ri rho ri dot instead of v, and plus dou by dou pi rho pi dot. So, that is the meaning of this divergence over here. As there are no sink or source for the phase points or for the representative points, the number of phase points within the volume must remain constant because there are no sink or no source within that volume, which means dou by dou t of the integral over tau rho d tau plus integral over tau divergence of rho v d tau must be equal to 0. This we write as dou rho by dou t plus divergence of rho v d tau integral over the total volume tau is equal to 0. Now, the necessary and sufficient condition that above integral vanishes for all arbitrary volumes tau is that the integral itself vanishes everywhere in the relevant region of phase space. So, we must have dou rho by dou t plus divergence of rho v equal to 0. Now, this equation provides the equation of continuity, if you remember from the hydrodynamics, equation of continuity for the swarm of the phase points or the representative points. So, if you write this divergence now, we get dou rho by dou t plus summation over I from 1 to 3n dou by dou Ri rho Ri dot plus dou by dou Pi rho Pi dot. This summation is for both the terms equal to 0. That is dou rho by dou t plus summation over I from 1 to 3n. Let's expand this. So we get rho dou Ri dot by dou Ri plus Ri dot dou rho by dou Ri plus rho dou Pi dot by dou Pi plus Pi dot dou rho by dou Pi equal to 0, and we remember that this summation is over all the 4 terms. Now this is dou rho by dou t plus summation over I from 1 to 3n Ri dot dou rho by dou Ri plus Pi dot dou rho by dou Pi plus, let's take rho outside, summation over I from 1 to 3n dou rho I dot by dou rho I plus dou Pi dot by dou Pi. So this is equal to 0. Now from Hamilton's equations of motion, from Hamilton's equations of motion, Ri dot is equal to dou h by dou Pi, and Pi dot is equal to minus dou h by dou rho I. So from here we can replace this Ri dot and Pi dot, and we can write then dou rho by dou t plus summation over I from 1 to 3n Ri dou rho by, rather it is Ri dot, this is Ri dot here, dou rho by dou Ri plus Pi dot dou rho by dou Pi, and for this term we write plus rho summation over I from 1 to 3n and dou by dou Ri of Ri dot is dou h by dou Pi, dou h by dou Pi, and Pi dot is substituted by minus dou h by dou Ri. So for this term we write minus dou by dou Pi into dou by dou Pi of dou h by dou Ri. So this whole thing is equal to 0. One can see that the two terms will cancel and we are left with dou rho by dou t plus summation over I from 1 to 3n ri dot dou rho by dou ri plus pi dot dou rho by dou pi is equal to 0. So we have obtained this equation. Now if we take total time derivative of rho, so d rho by dt, let's find. Remember, rho is a function of r, I and pi. So d rho by dt will be dou rho by dou ri dri by dt plus dou rho by dou pi by dpi by dt plus, to make it general, we will take rho as a function of time also. So we will get dou rho by dou t dt by dt. Now this will be summed from I equal to 1 to 3n, and that also summation will run for I from 1 to 3n. So d rho by dt we obtain as dou rho by dou ri dot plus dou rho by dou pi dot, both of them summed over I for I equal to 1 to 3n plus dou rho by dou t. Now this is exactly what we have here. That means from here we write this as d rho by dt equal to 0. And if you remember Poisson's bracket, this is Poisson bracket of rho, so that can be written as Poisson bracket of rho with h ri or over rp. You see, if you expand it, this is dou rho by dou ri dou h by dou pi plus rather minus dou rho by dou pi dou h by dou ri summed over I. In our case it is 1 to 3n, and dou h by dou pi will be ri dot. So now this becomes summation over I from 1 to 3n dou rho by dou ri dot minus, it will be plus because dou h by dou ri will be minus pi dot, so plus dou rho by dou pi into pi dot. So this is Poisson bracket of rho and h. So we can also write from here, because this is 0, we can also write from here as dou rho by dou t plus Poisson bracket of rho and h equal to 0. So from Liouville's theorem we finally obtain as d rho by dt equal to 0, or we write this as dou rho by dou t plus Poisson bracket of rho with h equal to 0. Now this equation or that equation, they are same. So this equation is called Liouville's theorem, And according to this theorem, the local density of representative points as viewed by an observer moving with a representative point stays constant in time. If you write this, so according to this theorem, the local density of representative points as viewed by an observer moving with a representative point stays constant in time. So, the swarm of the phase points moves in the phase space in essentially the same manner as in case of an incompressible fluid that is moving in a physical space. Remember that flow of an incompressible fluid is taken in a physical space. The motion of these phase points, motion of the swarm of these phase points is taken in phase space, not in any physical space. We have also mentioned that for a system in equilibrium, dou rho by dou t should be equal to 0, because there rho is not an explicit function of time, rho is function of r and p only. And from Liouville's theorem, we have found that d rho by dt is 0, or dou rho by dou t plus quotient bracket of rho over h, that is equal to 0. A distinction between these two equations must be made. You see, while this equation, which we obtained from Liouville's theorem, is derived from the basic mechanics of particles and is therefore quite generally true. So that is true in general for all the cases. While this first one, dou rho by dou t equal to 0, is only a requirement for equilibrium, which in a given case may or may not be true. Means this equation, which we obtained from Liouville's theorem, is true for any ensemble, whether that ensemble is stationary or not, whether it is representing a system in equilibrium or not, this is always true. But this condition, dou rho by dou t equal to 0, is true for such ensembles which are stationary ensembles, or such ensembles which are representing a system in equilibrium. So this dou rho by dou t equal to 0 is the condition for the systems in equilibrium, whereas this one, what we obtained from Liouville's theorem, is true for any system, means is true for any ensemble. For the simultaneous validity of these two equations, one can see that rho h, quotient bracket of rho h should be equal to 0, or in other words, summation over I from 1 to 3n of Ri dot dou rho by dou Ri plus Pi dot dou rho by dou Pi must be equal to 0. So for simultaneous validity of dou rho by dou t equal to 0 and dou rho by dou t plus quotient bracket of rho and h to be 0, quotient bracket of rho and h should be 0, or we can write this as summation over I from 1 to 3n Ri dot dou rho by dou Ri plus Pi dot dou rho by dou Pi must be equal to 0. One possible way of satisfying last equation, this one, is to assume that rho, which is already assumed to have no explicit dependence on time because dou rho by dou t equal to 0, is independent of the coordinates r and p also. So if rho, apart from being not an explicit function of t, it is also not an explicit function of r and p, then this condition will be satisfied, which means then the simultaneous validity of these two equations will be satisfied. So for that case, rho, which is a function of, in general, R and P, must be constant. And this constancy must prevail over the relevant region of phase space. And of course, outside that region, rho is 0 everywhere. Means within the relevant region, of phase space, rho is constant and rho is 0 otherwise. Means outside that region, rho will be 0. Within that region, rho will be constant. What does define which region of phase space is available to the system, or which region of phase space is relevant to the system? That is defined by the available microstates. You see, different points in the phase space represent different microstates of the system. So that region of phase space which is available to the system means that is a region of phase space where the microstate of the system are distributed for a given macrostate. Physically, this choice corresponds to an ensemble of systems which at all times are uniformly distributed over all possible microstates. So the equation of ensemble average then will reduce to the form F average is equal to 1 by the total volume tau, an integral of F, which may be a function of R and P, d tau, when this integration is run over the total volume tau. Remember, this tau is the volume of the relevant region of the phase space, as we have mentioned. As rho is not an explicit function of T, R or P in this case, so any member of the ensemble is equally likely to be in any one of the various possible microstates, in as much as any representative point in the swarm is equally likely to be in the neighborhood of any phase point in the allowed region of the phase space. Now this statement is usually referred to as the postulate of equal, we have mentioned it earlier, equal a priori probability. For the various possible microstates. So the resulting ensemble, the ensemble which develops this way, that is the resulting ensemble. So resulting ensemble is referred to as microcanonical ensemble. Microcanonical ensemble. So for microcanonical ensemble, the condition is that rho, that is the distribution function, rho should be constant in the region of phase space, which is the relevant region of phase space, and otherwise outside that region rho should be 0. So these two conditions are to be satisfied by a microcanonical ensemble, that rho is constant, for the relevant region, means where the microstates are distributed, and 0 otherwise. So outside that region, it will be 0. So that distribution function represents a microcanonical ensemble, or a microcanonical ensemble is represented by this kind of distribution function. We stop here for now. Next day we will find use of this microcanonical ensemble.